process in green plants and certain other organisms by which carbohydrates are synthesized from carbon dioxide and oxygen. Most forms of photosynthesis produce oxygen as a byproduct. In relation to this, the red equation for photosynthesis is water combines with carbon dioxide using light as a source of energy, which is then trapped by chlorophyll, will produce glucose plus oxygen. The red equation therefore is 6 molecules of water plus 6 molecules of carbon dioxide, still using light as a source of energy, which is then trapped by chlorophyll, will produce glucose plus 6 molecules of oxygen. The term rate, however, always involves time, so the rate of photosynthesis can be considered to be how fast photosynthesis occurs. This can be measured by the amount of glucose produced by a plant over a given time. However, in a process like photosynthesis, which involves more than one factor, its rate is limited by the factor which is closest to its minimum value. So at any point in time, if one of the factors is in low supply, this factor will be the limiting factor. Only a change in the limiting factor will cause an increase or decrease in the rate of photosynthesis. Changing the other two factors will have no effect. Therefore, the factors which affect the rates of photosynthesis include temperature, light intensity, that is, and its quality, and also carbon dioxide concentration and water. However, our main focus will be on the three main limiting factors, that is the light intensity and quality, carbon dioxide concentration, and temperature. Light intensity is the brightness of light. The rate of photosynthesis increases linearly with increasing light intensity up to an optimum light intensity point. So from this graph, we can see that the rate of photosynthesis is increasing linearly, that is from point A to B. That is its optimum light intensity point, and you can see that it is here it is 5. Gradually the rate falls off, and at a certain light intensity, the rate of photosynthesis becomes constant. So from B to C, we can see that there is no further increase in photosynthesis. Any further increase in light does not result in a corresponding increase in the rate of photosynthesis. That is from B to C. Since the other factors such as carbon dioxide concentration and temperature are limiting. In addition, light consists of wave particles possessing energy. The waves have different wavelengths. When light strikes the surface of a green leaf, some of the light is absorbed and some is reflected. A leaf looks green because it reflects green light. Also, my dress, for instance, absorbs more than one light. These different types of light, but because it's reflecting blue, because that's the color it's reflecting right now. The greatest absorption occurs in the blue and red parts of the spectrum. So from here we can see that an increase in the blue spectrum, that is 180 nanometers, and the red part, that is the 608 nanometers, will increase the rate of photosynthesis. Therefore, when the red and blue wavelengths are high, absorption is high and photosynthesis is high. In the same way, when the blue and red wavelengths are low, the absorption is low and photosynthesis is low. Now taking the next factor, which is temperature. Reactions constituting the Melvin-Calvin cycle, that is the dark stage of photosynthesis, involves enzymes. Temperature influences the activities of enzymes. An increase of about 10 degrees Celsius nearly doubles the rate of enzyme activity. The optimum temperature for photosynthesis in most plants is 30 degrees Celsius. But if the temperature rises above 40 degrees Celsius, which is the critical stage, the enzymes become denatured, and the rate of photosynthesis decreases rapidly and stops altogether. This is because heat energy causes more collisions between the enzyme and the substrate. Moreover, all enzymes are potent, and at very high energies, the proteins are broken down and no longer fit, and hence the reaction does not occur. So from this graph, we can see that an increase in about 10 degrees Celsius here, the enzyme starts to move. And at 30 degrees, that is the optimum temperature for most plants. It's active, it's very active. But then an increase in about 40 degrees Celsius, as a critical temperature, will kill the enzyme. That's a black indicating that the enzyme is killed. The active site of the enzyme becomes distorted and can no longer fit. That is why it is not being effective when the temperature is increased. And this is because enzymes involved in chemical reactions are temperature sensitive. That is also a reason. Hence, temperature favors the rate of photosynthesis. Now, taking carbon dioxide concentration, it is used to make sugar in the photosynthesis reaction. The concentration of carbon dioxide in the Earth's atmosphere varies between 0.03% and 0.04%. An increase in the concentration of carbon dioxide gives an increase in the rate of photosynthesis. The rate of photosynthesis of carbon dioxide from this graph increases linearly with increasing carbon dioxide concentration. That is from point A to B. Gradually, this one rate falls off, and at a certain carbon dioxide concentration, the rate of photosynthesis remains constant. That is from B to C, from this graph. Here, a rise in carbon dioxide levels has no effect on the rate of photosynthesis, as the other factors such as light intensity and temperature are now the limiting factors.
Supposing a plant A is placed in a room by a window, and a plant B is placed in an open field, assuming all other factors are constant, that is, water and carbon dioxide, plant B will have a higher rate of photosynthesis than plant A. With reference to the factor light, the intensity of light can affect the process of photosynthesis. Brighter light causes more light to hit the surface of plants, which increases the rate of photosynthesis. Thus, there tends to be higher rates of photosynthesis with climates in a lot of sun compared to those plants which are in predominantly dim places. The first step in photosynthesis is the absorption of light by pigments. Chlorophyll is the most important of these because it is essential for the process. It captures light energy in the violet and red portions of the spectrum and transforms it into chemical energy through a series of reactions. Therefore, with a higher light intensity, photosynthesis rate will increase until a different factor comes into play and becomes the current limiting factor. The chlorophyll in the leaf absorbs the light energy. Chlorophyll easily absorbs blue and red. However, it does not easily absorb green and yellow. It rather reflects them, thus the color of the leaf, giving the plant its green and yellow color. In relation to this, it can be concluded that plant B, which is placed in an open field, will have a higher rate of photosynthesis than plant A, which was placed in a room by a window, hence was lacking the appropriate amount of light needed to synthesize at a higher rate. The higher the temperature, the greater the rate of photosynthesis. This statement is not always true. To better understand the effects of temperature on photosynthesis, it is important to know the effects of temperature on the enzymes involved in photosynthesis. Enzymes are affected greatly by temperature. If the temperature is too cold, the enzymes move around too slowly to meet the substrate for a reaction to occur. However, if the temperature increases, so does the rate of the reaction, and it can be seen in this diagram, where when the temperature was low, there was no reaction or there was no activity in the enzyme. But when the temperature increased to 30 degrees Celsius, which is the optimum temperature for photosynthesis to occur in plants, there was a reaction, there was activity in the enzyme. But if you remember, all enzymes are proteins, And at too high temperatures, the proteins break down. So for instance, if the temperature increases from 30 degrees Celsius to 40 degrees Celsius, then it is a critical temperature and it will cause the enzyme to die, or it will cause the enzyme to become inactive, which will lead to no reaction at all. And to further explain this point, the active site of the enzyme becomes distorted, and so the substrate no longer fits, and hence the reaction does not occur, as you can see in this diagram. So we see that the enzyme has been denatured due to the sensitive nature of enzymes. But then greenhouses are used to capitalize on the effects of high temperatures, increasing the rate of photosynthesis. Plants from regions of warmer climates can successfully grow in colder regions by using greenhouses. Also, it affects the rate of